Today we're going to be talking about limiting reactants and theoretical yield. We will also be calculating percent yield, which uses our theoretical yield. We're going to start with some definitions. We've seen some skeleton reactions before, and so we're going to use today as an example, A plus B goes to C. We know the left side of the reaction is called the reactants. And then our right side is called the products. So in this case, we have two reactants, A and B. We also have one product, C. If we have the same amount of A and B, or even different amounts of A and B, whichever one is used up first during the reaction is said to limit the amount of product. And we call this the limiting reactant. What this means is if we start with, for example, 1 gram of A and 1 gram of B. If B's 1 gram gets used up and makes C, but there's still some amount of A left, B would be the limiting reactant. And I'm going to put LR under here. So in this example, the 1 gram of B gets used up. We've created C, and there's still some A left around. In this case, A would be said to be in excess. There's still some A around after all of the limiting reactant, or B, has been used up. Finally, the maximum amount of product you can make is the theoretical yield, and that is based on how much the limiting reactant can make. The reason for this is once all of B gets used up, A can't react anymore because there's nothing for it to react with. We see that A reacts with B and creates C. Once all of B's been used to make some C, all that's left in a beaker or in a reaction is A and C. The B's been used up, some C has been made, and A is just floating around in solution. So the amount of C that's made once B is used up is the theoretical yield. And we can do these calculations using both a balanced equation and the amount of the reactants. Let's do some examples. Here we have an equation with hydrogen gas, nitrogen gas, and ammonia. We have 3H2 plus N2 goes to 2NH3. I've also included up in the corner 2 squares from the periodic table to use for our molar mass. The first thing we need to do is we need to identify the molar mass and calculate it for all of the different compounds. So we need to do it for all the reactants and the product. In this case, we're going to calculate the molar mass for H2, N2, and NH3. The reason for this is because we are going to convert the 4 grams of H2 right here and the 2.5 grams of N2 right here. We're going to convert it to grams of NH3, which is ammonia, our product, and we're going to see which one creates the least amount of the product. That will be our limiting reactant, and that will tell us our theoretical yield. The way that we do this is we would go, and I'll use H2 as our example, we would go from grams of H2 to moles of H2, and that's what we're using these molar masses for that we're about to calculate. Then we go to moles of ammonia. We use our molar ratios for that. And then finally, we go to grams of ammonia. And again, we use our molar mass that we're about to calculate for that conversion. Let's do our calculations for molar mass. H2 is 2 hydrogens. So we would do 2 times 1.008 grams per mole. In that case, you would get 2.016 grams per mole. For N2, we're going to do something similar. We have 2 nitrogens, but in this case, our nitrogen molar mass is 14.007 grams per mole. So we would do 2 times 14.007, and we would get 28.014 grams per mole. And then finally, we have NH3. So we would do 14.007 grams per mole. That's the molar mass of nitrogen, plus 3, because we have 3 hydrogens, times the molar mass of hydrogen. So in that case, we would take 14.007 plus 3 times 1.008, and what we would get is, I'm going to run out of space, so I'm going to put it down here, 17.031 grams per mole. Okay, now we have all of our molar masses of our molecules and compounds. So H2 is 2.016 grams per mole, N2 is 28.014 grams per mole, and then NH3 is 17.031. So let's do our conversions now. We're going to start with the 4 grams of H2. We're going to convert this into grams of NH3. So we're going to convert both of these into grams of product. We always start by writing first our 4 grams of H2, whatever we're starting with, and put it over 1. Now, our next step, we go up here from grams of H2 to moles of H2. Whenever we're going from grams to moles, we use our molar mass. We calculated our molar mass for H2 over here. We know for 2.016 grams of H2 is 1 mole of H2. In this case, we want to put our grams on the bottom so that grams of H2 cancel out. So we would write it like this: 2.016 grams of H2 over 1 mole of H2. It's really important that we write grams of H2 and moles of H2 because that will tell us what we can cancel out. We can cancel out grams of H2 with grams of H2, but we couldn't, for example, cancel out grams of H2 with grams of NH3. Even though those were both grams, they're in different compounds. So it's only when it's grams of the same compound, moles of the same compound, etc. So our grams of H2 cancel out. If we were to stop right here, we would be in moles of H2, but we need to get to moles of NH3. Now for our mole ratio, I'm going to put down here our mole ratio. We're looking for moles of H2 to moles of NH3, our product that we're converting to. We're going to look at our coefficients. So we see 3 and we see 2. So for every 3 moles of H2, we can make 2 moles of NH3. So let's put this in here. We're going to put the moles of H2 on the bottom so they cancel out. And then we're going to put the 2 moles of NH3 on the top. Now, let's look at what cancels out. We have moles of H2 on the top, moles of H2 on the bottom. Right now, if we were to stop, we would be in moles of NH3, but we want to get all the way to grams of NH3. And in that case, we use our molar mass. We got that the molar mass of ammonia, or NH3, is 17.031 grams per mole. We're going to then put the grams on top and moles on bottom. The reason for this is we want moles to cancel out because we have moles on top right here. Okay. So our moles of NH3 cancel out. And right now, the only unit that we haven't crossed out is grams of NH3. And that's going to be what unit our answer is in, which is what we were going for. Now, how do we do this math? We're going to multiply everything on top and then divide by everything on bottom. So I'm going to circle in blue what we multiply. We're going to multiply 4 times 1 times 2 times 17.031. And then we're going to divide by 2.016, 3, and 1. So if we were to put this into our calculator, we would say 4 times 1 times 2 times 17.031. Then we would divide by 2.016, divide by 3, and divide by 1. And what we would get is 22.5 grams NH3. We're not going to worry about significant figures for right now, but we'll work on that in our next video. For the next one, we're going to do 2.5 grams of N2. So this is going to be very similar to what we did here. So I'll erase our H2 up here and add in N2. We're going to go from grams of N2 to moles of N2 to moles of NH3 to grams of NH3. We have 2.5 grams of N2 over 1. We always put it over 1 just so we can see that the grams of N2 are in the top, or grams of H2, or whatever your unit is. Putting something over 1 doesn't change the value. It's just like dividing by 1, it's the same number. Our next step is going to use the molar mass. Now, if we look in this first equation, we use the molar mass of H2. In this one, we're going to use the molar mass of N2. Just like before, we'll be putting grams in the bottom. And the reason for this is to cancel out the grams of N2. Now I'm going to write grams of N2. It's important we keep track of what compound or molecule we're using. Our grams of N2 cancel out. If we were to stop right here, we would be in moles of N2. But we want to get to moles of NH3. Now for our mole ratio, I'll do this one in yellow. Our mole ratio for N2 to NH3, we see 2 moles of NH3. But how many moles of N2? We see there's not a number right here. In this case, it's an implied 1. So this would be 1 mole of N2 to 2 moles of NH3. We put our 1 mole of N2 on the bottom and our 2 moles of NH3 on the top. Okay, in this case, our moles of N2 cancel out. And if we were to stop right here, we'd be in moles of NH3. But we want to get to grams of NH3. And this last step is going to be identical to the previous last step. We're going to put our 17.031 grams of NH3 on top and our 1 mole of NH3 on the bottom. Our moles of NH3 cancel out, and what we're left with again is grams of NH3. I'm going to circle in blue here what we multiply. We're going to multiply the 2.5 times 1 times 2 times 17.031 and then divide by 28.014, 1, and 1. So when we put this into our calculator, we're going to do 2.5 times 1 times 2 times 17.031 and then divide by 28.014 and then divide by 1, divide by 1. Now, in the divide by 1 cases or multiplying by 1, you really don't need to do that step because dividing or multiplying by 1 doesn't change the number. But for these, I am still going to circle them just so we can see where we divide and multiply numbers by, because oftentimes there will be numbers in those spots. In this case, our answer would be 3.04 grams of NH3. Now, we've calculated how much of the product each of the reactants can make. We see H2, if we have 4 grams of it, it could make 22.5 grams of NH3. However, the 2.5 grams of N2 can only make a little over 3 grams of NH3. In this case, we see that this one is the smaller number, and that tells us that our limiting reactant is N2. And it also tells us this right here is our theoretical yield. It doesn't matter how much of H2 we have right now, even though H2 can make 22.5 grams of NH3, it is in excess. The most that we can make, since we only have 2.5 grams of N2, is 3.04 grams NH3, and that's in perfect conditions. So this is our theoretical yield. This tells us in perfect conditions with 2.5 grams of N2, the most we can make is 3.04 grams of NH3. Now let's look at percent yield. So this was theoretical yield. And we're going to look at percent yield, and this uses our theoretical yield. Our theoretical yield was 3.04 grams of NH3. That was our theoretical yield. We calculated that on the previous slide. Now our question tells us that we used those 4 grams of H2 and 2.5 grams of N2, but when we did the experiment, we only got 2.8 grams of NH3. So our theoretical yield is the yield in absolutely perfect conditions. If everything goes perfect and you have 100% yield, you would get 3.04 grams. That's the most you can get. Now, when we actually do these reactions, we won't ever really get 3.04 grams of NH3. There won't be perfect conditions. In this case, we will have what's called an actual yield. And this is what this 2.8 grams is. This is telling us what our actual yield is when we went and hypothetically did this experiment. So to get our percent yield, we're going to put in these numbers that we have. You'll often see percent yield with a percent sign in yield as well. Our actual yield is what our question tells us we hypothetically found doing the experiment, which is the 2.8 grams of NH3. Our theoretical yield is what we calculated on that previous slide, our 3.04 grams of NH3. And then we would take these and multiply this by 100 to get our percent yield. So when we're putting this into our calculator, what we do is we do 2.8 divided by 3.04 times 100. And remember, for this video, we're not going to worry about significant figures. In this case, we find that we would get a 92% yield. So our percent yield, if we were to do this experiment, produce 2.8 grams of ammonia, with our theoretical yield of 3.04 grams, our percent yield is 92%. So in this case, we're now able to identify the limiting reactant, we're able to calculate the theoretical yield, and we're able to use our theoretical yield and calculate our percent yield.